Welcome to PGM session. I'm Zhao, a Huawei employee from China. I'm very excited that we have a chance sharing what we did on ARM platform and what ARM brings us, especially this year. The voice of ARM is higher than before, and more customers and service providers joined for extending ARM effective in the HPC industry. So ARM would be another choice for customers' data centers. Okay, my colleague Amit will start his session for the first part. Let's start.
Hi all, my name is Amit Khandekar. I have been working in PostgreSQL internals for more than 10 years now, and for the past 1 year as a Huawei employee, I have been working to make PostgreSQL better on ARM platform. Okay, now let's begin our presentation on PostgreSQL on ARM. Why ARM? The main reason is low cost of ownership. For the same price, more computing power can be bought. The second reason is today almost everything is available on ARM. The machines, the OS, database servers, web servers, and many other servers are ported on ARM. Big companies like Amazon, Huawei, Samsung, Apple, and Ampere manufacture their own ARM chips. ARM adoption is exponentially gaining pace in user space as well because it is now easily available on cloud. With that, it is high time that the software for high performance computing space leverages all the ARM capabilities and is optimized to run on this architecture. So same applies for PostgreSQL. So let's first briefly see what it means to optimize PostgreSQL from a developer point of view. Speeding up PostgreSQL on ARM. We already have PostgreSQL build farm machines on ARM, and we also have PostgreSQL packages available to download on ARM. So we know that PostgreSQL runs on ARM, but how do we go about making PostgreSQL faster on ARM? Here are some points which may help you work towards achieving the goal for faster PostgreSQL on ARM. Actually, these points apply to any kind of RDBMS, but for that matter, actually any kind of server. So first one, apply cost performance model before comparing performance on ARM versus x86. The key selling point of ARM servers is that with a given price, we get more CPUs. So it doesn't make sense to compare per CPU performance. Rather, we should check that for a given price, how much throughput we get with full resource utilization. Contention. Since the benefit of ARM is in its lower price performance ratio, it is critical that PostgreSQL scales out well with higher number of parallel clients. Otherwise, the high compute power will be a waste. That's the reason you should test and identify contention issues with high number of clients. Atomic operations should be optimized. These are again often high contention areas again. LW locks, spin locks, and various other scenarios use these functions that do atomic operations such as compare and exchange, increment, decrement, using compiler intrinsics or using optimized assembly code. So micro benchmarking should be done for such code scenarios to make sure they are not becoming the source of contention. And this does not apply only to atomic operations. Look for any kind of platform specific conditional compilation. You will see x86 specific assembly code at multiple places. At such places, usually for ARM, there is a fallback code which compiles fine on ARM, but it might not have been tested on ARM. The thing is, really a lot of testing was done for such changes before finalizing on the changes, but that testing was done mainly on x86. The fallback code might not have gotten so much attention or testing because earlier ARM was not so much a mainstream platform. So it's worth doing the same kind of testing of the fallback code on ARM. Next is compiler options and compiler versions. Be aware of what new ARM optimizations are supported by new compiler versions. For example, GCC 10.1 makes use of LSE ARM 8.1 instructions for functions such as atomic compare exchange or atomic fetch add. And Postgres has been reported to perform better in some scenarios without having to do any code changes, simply by enabling this LSE option during compilation. Numa awareness. So today's server class machines typically come with Numa support and multiple sockets. Cross-socket Numa access is quite expensive. PostgreSQL's shared memory is allocated upfront on single Numa node. So we have observed high contention when processes start accessing remote Numa nodes for LW lock structures. This needs to be fixed. SIMD vectorization. So always try to make use of Neon, that is ARM's brand for SIMD. Repetitive tasks such as PostgreSQL numeric multiplication has been found to perform much better on ARM if we make use of SIMD vectorization. Wherever possible, try to arrange for compiler auto vectorization also to keep the code portable. Then CPU cache line size. So typically on x86 the CPU cache line size is 64 bytes. But on ARM machines it may not be so. In fact, it is equally likely to be 128 bytes. So code that assumes cache size is 64 bytes may not work optimally. Now importance of query parallelism is especially more on ARM because typically on ARM machine has more number of CPU cores. So the processes running on ARM should leverage the fact that more cores are available. In other words, on ARM, it becomes all the more important that a PostgreSQL parallel query is able to scale out with more number of workers. Okay, so now that we saw how exactly we should go about improving things on ARM, let's watch Zhao explaining what all is being currently worked on with respect to PostgreSQL on ARM. Thank you.
Thanks, Amit. Okay, thanks so much about Amit's introduction. Let's continue with Amit to introduce more about ARM-related things in PG community. PostgreSQL is a worldwide open source community in database area. That's true. PG community is very open and accept any valuable proposal from outside. It accepts the ARM platform very quick and work with us together actively. Thanks to the years of ARM-related accumulation on PowerPC, it was a very smooth porting stage when ARM arrived PostgreSQL. Community provides the easiest way to support ARM. Release the ARC64 package officially. From 9.5 to the latest 13 version, and two major types packages, Debian and RPM for multiple OS. So thanks PG community for such support. And besides this, we also introduced some ARM-specific optimizations into PG community for increasing the performance on ARM platform. Go through the full PostgreSQL hacker mail list history. I searched with the keywords ARC64. There are several discussions about ARM. We can see the first one was raised in 2018 and the second one raised in 2020. There is a 2-year interval. But in 2020, there was a lot of discussion and revision about ARM in PG community. And in this year, the work would be continued. Not only PG community, seems the whole open source world start to play with ARM. Now, let's see what gain we can get from these optimizations. Let's pass through the whole ARM-specific discussion and optimization in community and see what we gain from ARM, and this would help customers to feel confidence. The first one is reducing the core stack about several top-level functions for getting more performance about the store procedure. This also works on x86, but a visible improvement on ARM. The second one is spin lock optimization. The spin lock is a well-known issue about performance. Actually, we are talking about the CES and TAS. In compare level, TAS will write directly, but CES will first to compare, if match, execute the write operation. Due to write is cost, so in the case of high concurrency and using lock frequently, That would be a good way to improve the performance. On x86, it uses the optimized exchange operation to do it, but on ARM, it becomes to support it in ARM version 8.1, so we cannot apply it on ARM version 8 machines. But there is an alternative, which we discussed in PG community. GCC 9.4 supports for outline automats that allow us to make it customized. After patched, there is a 10 to 40% gain in simple update and TPCC lag cases in our PG bench tests. The third one is benefits from O3 option of GCC. It brings many vectorization algorithms to improve the speed of parallel execution relies on the utilized pipeline and cache of CPUs. The same with ARM chips. The case we covered in these optimizations is about vectorized the loop tree. The set option is tree loop vectorized in O3. From PG source code, we found there is some loops could be optimized in this way. I mean from a complex loop to a simpler loop, which GCC can apply vectorize automatically. In this optimization, we got 2 more times gain for multiplication of numeric taps on ARM. The next one is introducing a way to process 64-bit tracks instead of bytes. So the reason we introduced this about how the CPU process its data at time. For ARC64 and X84, it's 64 bits. That means the CPU can execute with the whole 64 bits data quicker than splitting them by taps. In guest index building cases, there is a 30 to 60% gain, including creation, updation, or insertion cases. The last one is introducing outline atomic option of GCC during configuring PG software for making sure the underlying hardware can use the appropriate instruction during running time. So all of this optimization sounds attractive, but some issues are still waiting for resolve. Let's see. Most of these are related with the compiler options. What we can do for PostgreSQL itself. I mean features or other things. Right. We cannot just rely on the compiler. We should also enhance the software. The development of database has evolved from traditional databases, which provide a single node, to active standby development, then RAC cluster. People discovered the scalability issue, then databases and tables sharding by DB middleware. In the end, to the distributed databases, the more requirements are from OLAP cases. Consider that ARM gives us more resources. For common multiple Numa architecture, that means more Numa nodes, and ARM processors doesn't support hyper-threading technology, so it won't work like x86 for now. So both bring some challenges for the optimization work. For more Numa nodes, we should take care of threads to access across Numa nodes, and that's true if we don't customize the OS scheduler configuration, so the OS will schedule the memory location randomly on each Numa node. That's a high priority for access Numa cases. This will bring a bad or unstable performance in most of user cases. Then, how we can leverage these resources for performance would be the big problem. Let's try to image a basic case. There are some state variables or structure in our software. Note that most of software needs this kind of data types for connecting each thread. To keep sequencing or resolve resources, such as a global counter or a global lock. Right now, we have two Numa nodes machines. They are Numa node 0 and Numa node 1. Thread 0 and thread 1 locate on different Numa node and run on different core. The state variables locate on the host memory. When they want to read the state variable, that would be okay. But when they try to write or update the state variables, there will be a contention situation, especially in high concurrency cases, and if thread change a struct. For example, changing the different part of a single structure instance, and at the same time, both data are loaded into one cache line. That will raise a cache line for sharing and increase the contention. In the end, affect the whole performance. So the possible approach is introducing a partitioned state variables. Threads on different Numa node just access its partitioned part, which locate the same Numa node with threads. This way will reduce the contention, but would be a challenge to how to manage this kind of partition construction. Just like Amit's introduction, this would be fixed in PostgreSQL when it runs on ARM. For the OLAP cases, the scale of development becomes larger. Serialized task processes are gradually replaced by the parallelization for increasing resource utilization. We can see the picture. It is very similar with machine learning, including source data partition, operator application, and the result data collection. But this is OLAP cases. This scenario is common in big data and AI. Therefore, the database software that carries data needs to be changed. For traditional OLTP open source databases, I think PG did a good job. It supports parallel query for a long time. Parallel query is more important for ARM platforms. Here are some TPS figures for a PG bench test that was run on an ARM 64 machine and an x86 machine. Cost performance model was used to derive how many CPUs each of the machines should be allocated. So, for the same price, it came out to be 64 CPUs on ARM versus 28 CPUs on x86 machine. With this, you can see that with higher clients, TPS figures on ARM were on par with x86 figures. In fact, due to higher available CPUs on ARM, we are able to scale beyond the x86 figures with more than 50 numbers of clients. In the second graph, we get similar kind of graphs for TPCB-like workload as well, and you could see the benefit of the spin log patch even in this workload. Okay, in the end of talking, let's see the whole ecosystem of PostgreSQL. More and more software support ARM platform. From now, even if we see the Postgre can run on ARM efficiently, No one can guarantee that all these components will run on ARM properly in our real commercial scenarios. There is a long way to go and much work remains to be done. Note that we only put several of them. Many organizations or communities support ARM spontaneously. This population effect is exactly what we hope, but the work is huge enough. We still need to work in advance and work at the right time to follow the trend. Okay, thank you for watching. Any questions you want to ask, please raise them in the channel. We are welcome that answering the questions and making the channel more active. Thank you very much.